So thank you all for attending this week's Applied PD seminar at the University of Washington. I believe all of us have plenty of experience, more than we probably want with online seminars. In this case, if you want to ask questions during the talk, feel free to unmute yourself or to put questions in the chat. And of course, there will also be questions at the end of the talk. Our speaker this week is our own Anastassiya Semenova. Anastassiya got her PhD from the University of New Mexico before going on to a postdoctoral appointment at ICERN in Rhode Island. And then she is now in her first year of a postdoc here at the University of Washington. And she'll talk to us about the instability of Stokes waves. Thank you, Anastassiya.
Thank you very much, everyone, for attending. And I would like to thank Bernard for giving me the opportunity to speak at the Applied PD seminar at UW. I'm very happy that we can present our work here. So today,
so actually, Anastassiya, if I may quickly interrupt.
Yes.
I should have said as part of my introduction that I really want to thank Anastassiya for she is actually in terms of all the practical matters for the seminar, and she's really the main organizer of the seminar. So thank you for that.
Thank you very much. It's a pleasure to organize it and speak and meet all of the people, and I hope we will continue doing that. Okay, so I will be speaking about, I will continue this talk as a continuation of the talk that was given last week by Sergei Dichenko. So I will be speaking about instability of Stokes waves, and in particular about an infinite depth case. So I started working on water waves problem when I was a graduate student. So I would like to mention all of the collaborators that I had during the years while working on the problem of water waves, and in particular Stokes waves. So Pavel Lushnikov and Alexander Kratkevich, my PhD advisors from University of New Mexico, also Sergei Dichenko from State University of New York at Buffalo, and now I'm also working with Bernard Dikonik from University of Washington. And for the finite depth water wave problem, we are also having a graduate student from University of Washington, Eleanor Burns. Okay, so the waves we are interested in studying are presented in both of the pictures that we have here. And you can see my mouse, right?
Yes.
So the left photo is a photo from the Netherlands at Maas-Waal Canal, and the photo on the right is from a US Army near the Panama coast. What we see is that these waves in the transverse direction are the same. So this is the waves that we are interested in. And instead of considering a 3D problem, we would like to consider a 2D problem. The fluid that we are interested in will be ideal fluid. We will have a free surface and also infinite depth. So free surface would be represented by a one-dimensional curve that we are going to refer to as eta. And then x and y would be spatial variables and t would be time variable. Also, the fluid would be acted upon by the force of gravity, and we would disregard the effects of surface tension for everything that we showed today, and also atmospheric pressure. Also, the flow, we consider the potential flow with the velocity potential of phi. And we will assume that the free surface and velocity potential phi to be 2 pi periodic functions in the variable x. Okay, so after these assumptions, we arrive with a famous water wave equation where we have a Laplacian inside of the fluid, and then we have the following 3 boundary conditions. That have been mentioned in all of the previous talks during this spring seminar series. So the first one is just a kinematic boundary condition on the free surface. The second is a dynamic boundary condition on free surface. And in addition to the 1 and 2, we will also have a condition at the bottom of the fluid that a fluid cannot pass in the vertical direction at the bottom. Just for simplicity and for future references, we are going to refer to the potential on the free surface as psi of x and t. So as was mentioned in the previous talk, we would like, instead of solving this problem on the boundary that changes in time, we would like to consider the so-called time-dependent conformal transformation, z of wt. And without going into the details, what it does, it maps the region from -infinity to 0 and -pi to pi in the w plane into the fluid domain. And in particular, line v equals to 0 is mapped into the free surface of the fluid. And after the following, after considering this conformal time-dependent transformation, we can rewrite the equations of motion in the W domain. So this was done in 1973 by Ovsyannikov and later independently by Vladimir Zakharov, Alexander Dichenko, and Evgeny Kuznetsov in 1996. Both of these implicit equations of motion are posed on the real line, and basically the first equation of motion corresponds to kinematic boundary condition, and the second corresponds to the dynamic boundary condition. And here there is an operator h hat, which is just a Hilbert transform. And in the Fourier space, the way we apply it is just by multiplying by I sigma k. Okay. What we are interested in studying Stokes waves. Stokes waves are traveling wave solutions of these equations. There are important properties of Stokes waves that I would like to mention, that are important to mention today. So first of all, they're finite amplitude periodic traveling waves. They're moving without change of shape and with the same velocity. We are going to define the height of the wave to be the distance between crest and trough. And then the steepness of the wave that we will be referring to as S is going to be the ratio of height over the wavelengths of the Stokes wave. Okay. It was shown that there exists a limiting Stokes wave that is a wave of the greatest height. And there is an angle forming at the crest for the limiting Stokes wave. And an angle of 120 degrees. Another important property of Stokes waves is that velocity of Stokes waves and Hamiltonian as functions of steepness of these waves oscillate. So in this next couple of slides, I will be showing the plot of these oscillations. So on the horizontal axis, we show the steepness of a Stokes wave, and on the vertical axis, we show the velocity. So as the steepness increases, that is, as we are approaching the limit in Stokes wave, if we zoom in into this region here, we see that, first of all, we have a first maximum. But at the same time, if we start to zoom in into this region where it looks like we have a minimum, we do indeed get a minimum. And if we can, but we see that we have another maximum. And if we would continue doing that, if we would zoom into this region, we would get a second maximum, then we would get a second minimum, and so on. And in this table down below, I'm just presenting the first 4 extrema of velocity and the corresponding the values of steepness at which this extrema occur. One important note is that the maximum in velocity as a function of steepness occurs after the maximum in Hamiltonian as a function of steepness. So now if we look at the plot of Hamiltonian as a function of steepness, the first maximum appears for the steepness before we had the first maximum in velocity. But again, if we continue along this curve, what we would see as we would zoom in into this region, we would have the first maximum of the Hamiltonian, then minimum, then once we zoom into this region, second maximum, and then once we zoom in more, second minimum, and so on. And in this table, I'm showing the first 4 extreme of Hamiltonian as a function of steepness. Okay, so this is important values of steepness that we're going to get back later in our talk. Now, let me just mention how we set up the problem. Full details are described in the previous talk by Sergei Dichenko, but let me just very briefly mention that to study stability of Stokes wave, we rewrite equations of motion in the moving frame that moves with the velocity of a Stokes wave. Then we linearize this equation around the Stokes wave solution and end up with the following 2 equations, where delta phi and delta y are perturbations of a Stokes wave. And these 2 equations can be rewritten in the following matrix form, where L hat and M hat are operator matrices with some nice properties. So M hat would be self-adjoint and L hat would be invertible by hand. And then what we would need to do, we would just pose an eigenvalue problem. So we would consider the following ansatz in the form of e to the lambda t, where lambda would be a complex eigenvalue. And if the eigenvalue would have a positive real part, then it would mean that the perturbation grows in time. And then, of course, the eigenvalue problem can be rewritten in this form, and we can solve this problem numerically. So I just skip all of the details. They are described in the previous talk. Now I can go into the main results that we got. Okay. So for the next couple of slides, I'm going to present the eigenvalue spectrum, meaning that on the horizontal axis, I will be presenting the real part of eigenvalues that we computed, and on the vertical axis, I will be presenting the imaginary parts of eigenvalues that we computed. And every next slide will correspond to the Stokes wave with a higher and higher steepness. That is, as we are going further and further from the slide, we will be approaching the limiting Stokes wave. Okay, so we start at a almost flat surface. So this Stokes wave is almost linear. As expected, we get the Benjamin-Feir instability, or figure 8. As we increase the steepness of a Stokes wave, what we would see and what we expect to see is that the figure 8 grows. This is indeed the case. But what is interesting, as we would go further, as we will consider even steeper Stokes wave, the shape of the figure 8 would start to change. So now it would start to resemble something that looks like an hourglass. And in the end, these 2 pieces of figure 8 would separate. And as we will continue increasing the steepness of a Stokes wave, around which we linearize our equations and for which we find eigenvalues, these 2 remnants of Benjamin-Feir, they would actually shrink in size. So they would get smaller, and there would be nothing at the origin. So this would continue for quite some amount of Stokes wave, but at a particular value of a Stokes wave, there would be something that would appear at the origin. So these are the remnants of the Benjamin-Feir that are located here. They are still shrinking in size, but now we have a small ellipse appear at the origin. And as we would continue increasing the steepness of a Stokes wave, sorry, that was a wrong key to press, the ellipse actually would get larger in size. And the eigenvalue with the largest real part would now be located on the real axis, on the horizontal axis. So it is not part of the Benjamin-Feir anymore, it is part of this ellipse. And I would like to mention that the Benjamin-Feir still shrink in sizes. And what it starts to do, it actually starts to move toward the origin. So these remnants of Benjamin-Feir start to shrink in size and start to move toward this ellipse. So the ellipse grows, still grows. Benjamin-Feir gets smaller and approaches the origin. Also, I did not mention before, but at the same time, we are also able to compute the high-frequency instabilities. They are not presented on this slide or on any of the slides, but they're actually located on the imaginary axis here and here. We're just not showing them today. Okay, so now for my next slide, this will be the same Stokes wave, so the same eigenvalue spectrum. I'm just going to rescale the horizontal axis. So this is the same result, except that this time I just rescaled my horizontal axis. So somewhere here I have minus 0.2, and somewhere here is about 0.2. So what we would see, so this is our the remnant of the Benjamin-Feir, if we call it that. But if we would continue to increase the steepness of a Stokes wave, this ellipse would increase, would get larger and larger in size, and then eventually it would start to get squished at the along the horizontal, along the vertical axis. So it would get this somewhat peanut shape. And at the steepness of a Stokes wave corresponding to the maximum of the Hamiltonian, we would get a figure infinity. So what is this green and yellow eigenvalues? So the green eigenvalue corresponds to the Floquet parameter mu equal to 0. That is a perturbation with the same period as a Stokes wave, so co-periodic. The red circle corresponds to the eigenvalue with double the period of a Stokes wave. That is a Floquet parameter equal to 1/2. So I would like to mention this is extreme of Hamiltonian. This happens at the extreme of Hamiltonian. We still have not hit the extrema of velocity of a Stokes wave. If we continue increasing the steepness of the wave, the figure infinity would split, and we would get these two, we can call them ellipses, even though we will see very quickly that they will be doing very interesting things. But the two remnants of figure infinity will split, separate, and they will actually start to move along the horizontal axis, away from the origin. And in all of the plots that I will be going to show you further, I will concentrate on this right localized instability. So we call this a localized bubble of instability. So I will just concentrate on this one here. So as we are increasing the steepness of a Stokes wave, this bubble, this localized instability, moves away from the origin. It shrinks in size. But what is interesting is that it starts to change the shape. And another thing to look at is what happens with the co-periodic and perturbation and the perturbation with the double period of the wave. So right now, the most dominant eigenvalue, that is eigenvalue with the largest real part, correspond to the perturbation with the double period of the wave. So this red eigenvalue. So we are moving further and further away from the origin and approaching a limiting Stokes wave. And what we see is that the co-periodic perturbation really wants to catch up with the perturbation that has double the period of the Stokes wave. And actually, it wants to become the dominant one. it wants to become the eigenvalue with the largest real part. And it is going to happen. So this is a snapshot where these two eigenvalues are very close to each other. So if we zoom into the region here, we see that the eigenvalues with Floquet parameter mu equals to 0 almost catch up with the eigenvalue with the Floquet parameter mu equals to 0.5. And actually, the coperiodic, or as we sometimes call it, superharmonic instability, now becomes the dominant one. That is, the real part of this eigenvalue is the largest of them all. And the perturbation that has doubled the period of a Stokes wave now is going to get moved further and further away from the mu equals to 0. So at the same time, I would like to mention that this bubble is moving away from the origin and gets smaller in size, as we will see in a bit. So now they're once again far apart, but the eigenvalue corresponding to this red circle is not very happy that it's not the dominant eigenvalue now, and it wants to get back at being the dominant one. And if we would continue considering Stokes wave with higher steepnesses, what we would see is that this localized instability would start to get very interesting shapes. It would start to shrink in size very, drastically. So if we look at the vertical axis compared to the previous range of values, we see that the localized instability became very small. But what is interesting is that the red, the eigenvalue corresponding to the red circle, eventually will catch up with the green one, and it will overtake it. So it will become the eigenvalue with the largest real part, and corresponding to the Floquet parameter 1/2. And then the Floquet parameter corresponding to 0 would be just this green circle. But what we would conjecture is that as we are moving along toward the limit in Stokes wave, this interchange of which one is the most unstable will continue infinitely many times. And we will always have either the with double the period of a Stokes wave to being the most unstable one, or a perturbation with the same period as a Stokes wave. So those two, either mu Floquet parameter equal to 0 or Floquet parameter equal to 1/2. Now let's look at the plot where we just track the location of the eigenvalue with the largest real part as we increase steepness from almost linear waves to the as close as we can get to the limiting Stokes wave. Here, I would like to mention that we compared our result to the result of Franklin and Bernard-Koenig, their analytic result. I think now it is already published in the Journal of Fluid Mechanics in 2023. So their result works very well in the regime of almost linear waves. And this blue line here corresponds to the result from Creed and Koenig. And we saw that our numerical results coincide very well with their analytical curve. We have the green curve and the red curves are our numerical results. Also, sorry, I forgot to mention that on horizontal axis here, we have steepness of Stokes wave, and on the vertical axis, we have the largest, the eigenvalue, the value of the eigenvalue with the largest real part. We have these two different colors, green and red. What do they mean? So the green curve corresponds to the value, to the largest value of real part of eigenvalue, while it is still located on the Benjamin-Feir, on the very on the primary Benjamin-Feir or the remnant of Benjamin-Feir. So basically, it is still somewhere here, okay, or here. And as we saw, the remnant of Benjamin-Feir would shrink in size and eventually disappear. And at some point, the ellipse at the origin would become so large that the eigenvalue with largest real part would become the most unstable one. This happens at the value of steepness S2 presented here. And so that we are still far away from the maximum in velocity with steepness at this point. And we are kind of a little bit past the halfway to the maximum in extreme of Hamiltonian. So if we zoom out of this region here of Stokes wave that are not too steep yet, and if we rescale our horizontal axis, what we would see is that this eigenvalue that first appeared on the ellipse would continue to be in the most dominant one. So on the vertical axis, we have the real part of the real part of the eigenvalue is the largest real part. And what is interesting here is that these points here correspond, so points E, F, G, H corresponds to the steepnesses at which figure infinity forms, and then the two localized bubbles appear. So this is the maximum in the Hamiltonian. If this region here, where we have the points I, J, K, L, is the localized instability that I showed you, that where we had interchange of this between the coperiodic perturbation and perturbation with double the period of Stokes wave. So basically, at the point L, the most unstable, the eigenvalue with the largest real part is now coperiodic. So it has the same period as a Stokes wave. At point I, it is the largest, the eigenvalue with the largest real part has double the period of a Stokes wave. In this region here, so the points M and OP, this is where the switch happens again. So at the point M, the most dominant eigenvalue corresponds to coperiodic perturbation. And at the point P, the switch already happened. So the most dominant eigenvalue now has the double the period of a Stokes wave. Well, what do we see is that as steepness increases, this curve goes to infinity. And actually, I wanted to include this plot from previous research where I just look at superharmonic instabilities, that is perturbation that have the same period as a Stokes wave. So on this plot, there is just some rescaling on horizontal axis, but basically this is a steepness. And on the vertical axis, we have just a square of eigenvalue. So this eigenvalue is purely real. Floquet parameter corresponding to it is mu equals to 0. And we show first 3 coperiodic instabilities. And the plot is in the log-log scale. Why do I show it? Is we see that as I'm approaching a limiting Stokes wave, which correspond to the points to the eigenvalues here, their behavior is approximated by the following power law: 1 over S max minus S, so lambda squared. S max here is a steepness corresponding to the limiting Stokes wave. So it means that we have, if we return back, since we conjecture that the switch between coperiodic and the double period perturbation continues to happen as we are approaching the limiting Stokes wave, we conjecture that we have the infinite growth rate. And it's not physical. So basically, it is telling us, indicating that our model breaks down, and at some point, we need to start considering the surface tension. And in particular, we computed that it would correspond to the steepness of Stokes wave being somewhere, if you look at this plot, somewhere in the region here. So this is wavelengths of 50 and 100 meters. That would be a steepness of a Stokes wave of about 0.141 and even further 0.141 or 3. So way past where we are currently located. So in this regime, we would need to include the surface tension term. S max 2 here corresponds to the maximum of the Hamiltonian, second maximum of the Hamiltonian. S mean is the first minimum in Hamiltonian as function of steepness. Another interesting remark is that, well, there are these coperiodic perturbations. We have first one, second, and third. What does it mean? Actually, if we go back to the origin in the spectrum, what we would see is we would see a secondary Benjamin-Feir appear as localized instabilities away from the origin along the horizontal axis. We have a second Benjamin-Feir or second figure 8 appear. And it goes through the same stages as the first one, which I have here. So it splits. There is a second ellipse, secondary ellipse appear here. There is a second figure infinity appear that also splits. And we have second localized instabilities. So second small bubbles moving away from the origin. In addition, there is a third one that we can compute too. So there is a third figure 8 appear at the origin, and it goes through the same stages as the first one and the second one. Meaning that the secondary and third localized branch appear. So this localized third and third bubbles appear, move away from the origin, while the primary one, the one that we are tracking here, is still moving away from the origin. Okay, so we conjecture that this new figure 8 instabilities and new localized instabilities appear infinitely many times as we are approaching the limiting Stokes wave. Okay, let's see. Okay, now next I would like to look at the eigenfunctions. So now I'm returning back to the primary Benjamin-Feir, primary figure infinity, and primary localized instability. So everything before these two cases. So we consider the steepnesses before these two guys appear. In this plot, we present the eigenfunction corresponding to coperiodic perturbation, the one that is in the red color here. And then we also are showing the eigenfunction corresponding to the perturbation with a double period of the wave. That is a green curve here. Since those are the one that are the two most unstable eigenvalues, or the eigenvalues with the largest real part. And what we would see as steepness increases of a Stokes wave, these eigenfunctions would become increasingly localized near the crest of the wave. Next, what we would like to do is we would like to compare this result to the nonlinear dynamics. So here, a black solid line is just a Stokes wave that we consider for the time simulations. The yellow and green curves, also the blue and purple ones, if we zoom into this region, so this is an inset into the green curve, those are just the time dynamics, time evolution of a Stokes wave. as an initial condition. And the black dotted line here that is on top of this red line is just a Stokes wave perturbed with the most unstable eigenfunction. And we see that it matches pretty well the early stages of the time dynamics of a Stokes wave in a dynamical code. And basically, what we would like to state that this profile at the early stage coincides pretty well with the time dynamics of a Stokes wave. And we expect that this leads to the overturning of the wave. Okay, so I think I have about 10 minutes. Let me briefly go over the summary. So we are able to compute to study the stability of Stokes waves from very small, almost linear waves to an extremely steep waves by using a variation of the Fourier-Floquet-Hill method. As was shown, we are able to see the Benjamin-Feir and superharmonic or coperiodic instabilities. I did not show that, but we are also able to compute high-frequency instabilities with this method. We showed that the dominant eigenvalues, that is, eigenvalues with the largest real part, correspond to the perturbations that are either coperiodic with the Stokes wave or have double its period. And then we also showed that instabilities that dominate the dynamics are localized near the wave crest. Of course, next thing that we would like to do is work in more details on high frequency for the infinite depth case. Of course, we are very much infinite in studying the same problem in the finite depth case, and we're having help. So the work is done, majority of the work is done by the graduate student, Eleanor Byrne. Another thing that we can do is to consider a different conformal transformation that would allow us to consider even steeper Stokes wave. Right now, we do not have it yet. Of course, it would be very interesting to add surface tension and see what is going to happen for Stokes wave, where the surface tension terms start to play important role. And of course, if we can add vorticity, that would be also a very interesting problem to look at. Okay, and I think I have about 10 or so minutes. So before I finish, I just want to briefly mention the finite depth problem, the setting for the finite depth problem. So not for the stability question, but just for the Stokes waves themselves. So we can study the two-dimensional ideal incompressible fluid, also with free surface eta, but this time we can add a finite depth, y equal to minus d. We would also assume the fluid to be ideal, and we would also assume that the flow is potential with velocity potential v. So, and of course, for now, we are disregarding effects of surface tension and atmospheric pressure for the finite depth case too. So we also consider the conformal map technique. We would use conformal map technique to map the rectangle in the W plane from the minus IH to V equals to 0 and minus pi to pi in U variable into the fluid domain. If we would do that, we are able to compute a Stokes wave, the following Stokes wave, Stokes wave. So for example, if we fix a complex depth of 1.5, we are also getting a Stokes wave whose steepness is increases, and there seems to be a corner forming at the crest. And also, as we had for the infinite depth case, we would have the oscillations in velocity as a function of steepness and oscillations in Hamiltonian as a function of steepness. Okay. In addition to that, by using this method, we also can find the solutions that look like cnoidal waves. So if we would decrease the depth of the problem and velocity of our solutions, starting from a Stokes wave, we would be able to get something that looks like a cnoidal wave. And of course, now it would be very interesting to study not just the stability of Stokes waves, as we've been doing for the infinite depth problem, but also for the cnoidal waves in a finite depth problem. Okay, and this is it. Thank you for your attention.
Thank you, Anastassiya. So let's stop the recording and let's see if there. Well, I'm sure.